Hi class, welcome to the moles and stoichiometry review. Again, like all reviews, we have the key ideas in bold. We have sample questions below. Let's begin with question number 1. Question number 1 asks us to find the formula for copper 2 hydroxide. Now, when we look for our elements, we can use our reference table to find the symbols that would go with copper and hydroxide. Let's take a look. So when we look at reference table S and we look down to element number 29, we can see that copper has the symbol Cu. Now, when we look for the element hydroxide, we'll see that there is no element that is called hydroxide. Now, in chemistry, the ending IDE is kind of like a period. It signifies the end of an element. So we might say something like chlorine we'll call chloride, as that will be the ending of a compound. But there's nothing that is called hydrox here. So we'll have to look elsewhere on reference table E for hydroxide. Here on reference table E, we find hydroxide has the symbol OH, and it has an oxidation state of minus. Now recall in chemistry that we don't write ones, so a minus sign indicates a -1 charge. So let's go back to the question. In this case, we are given copper 2 hydroxide. Now we know that copper has the symbol Cu, and hydroxide has the symbol OH. Now, when elements form compounds, they arrange themselves so that their net charge is equal to 0. Therefore, they'll be most like a noble gas. The charge of hydroxide is -1. And here in Roman numerals, we're given the charge of chlorine as a Roman numeral 2, +2. Recall that an easy way to write formulas is to write the oxidation numbers and then cross them. So copper 2 hydroxide is going to require 1 copper and 2 hydroxides. So when we indicate 2 hydroxides, we want to make sure that we have not just 2 hydrogens, but 2 of these entire ions, so we'll place it in parentheses. So choice 4 is the best choice for the formula of copper 2 hydroxide. In question 2, they ask us about a compound whose formula is XBr3. And they ask us, well, where on the periodic table can we find X? So in this case, we have the symbols of X and bromine, and we have the subscripts. The subscripts of bromine is 3, and there's no subscript for the X, which means it is 1. There are 2 ways to essentially solve this problem. First, let's refer to our reference table. Here on our reference table, we'll find bromine has an oxidation state of -1. So we can see that the oxidation state of the bromine, the 1, was crossed over to the X. That means that the oxidation state for X, which we're looking for, must be crossed over from the bromine. So here we believe that the oxidation state of X is +3. Now the other way to answer this is again to look at the formula and write in the subscripts and the known oxidation number. Now the oxidation number of X is unknown, but what we do know is that when we multiply the absolute values of the subscript and oxidation numbers, they should be equal. So in this case, it's some unknown value times 1 would equal 1 times 3. And in this case, we have the charge of +3. Now we need to find which group. Now groups on the reference table are labeled here as columns, would have an oxidation number of +3. Group 1, everything has an oxidation state of +1. Group 2, everything has an oxidation state of +2. And in group number 13, we can see several plus 3 oxidation states. So in this case, group number 13 is the correct answer. You can see here in group number 14, the oxidation states of 4 and 2 dominate. In question 3, we're looking for the empirical formula. Now, empirical refers to laboratory, found in a laboratory or proved in a laboratory. And in a laboratory, formulas are proven to their lowest common ratio of atoms. So here we have C6H12O6. What we need to look for is the greatest common factor between 6, 12, and 6. And so the greatest common factor would be 6. So if I took all of these subscripts and divided them by 6, I would be left with CH2O. Question number 4, we're given that naphthalene has an empirical formula of C5H4 and a molecular mass of 128. They ask us to find the molecular formula. So here, again, the empirical, the reduced formula is C5H4. And we're asked to find the molecular formula. The molecular formula could, in fact, be the empirical formula. Or it could be some multiple of the empirical formula, like C10H12, or if we multiplied by 3, it would be C15H12. And so we could do guess and check for this, but the easiest way to do this is to first find the empirical mass. So to find the empirical mass of C5H4, we're going to take 5 times the mass of carbon from our reference table plus 4 times the mass of hydrogen. So let's pull up the reference table. So here on the reference table, we'll want to round masses to the 10th place. But we can see that the mass of carbon, 12.011, rounds to 12.0 when we round to the 10th place. And the mass of hydrogen, 1.0794, rounds to 1.0. So when we do this math, we end up with an empirical mass of 64. But we have a molecular formula of 128. Remember that the molecular formula is just some whole number multiple of the empirical formula. So the next step would be to divide the molecular mass, in this case 128, by the empirical mass to find the whole number ratio, which is 2. So that means that our empirical formula is multiplied by 2 in order to discover the molecular formula. So our molecular formula is 2 times C5H4, and that is equal to C10H8. For question 5, we were asked to balance the chemical equations to the smallest whole number coefficient. When balancing an equation, the easiest way to do this is to take an audit of the species you have on both sides. So I would like to take my audit directly below the arrow, as it separates the reactants on the left from the products on the right. So here we have copper, we have silver, then we have a polyatomic ion nitrate. And I notice that my nitrate, NO3, is in its polyatomic form on both sides. Because of that, I'm going to take a shortcut and account for my polyatomic ion as one single unit. I could, however, go and account for it as separate atoms of nitrogen and oxygen. If I did separate atoms of nitrogen and oxygen, on the reactant side I have 1 nitrogen and 3 oxygens to begin, but on the product side, since it's in parentheses, I will distribute this 2, So I would have 2 nitrogens and 6 oxygens. So let's go and do our initial audit. Initially, we'll see that on the reactant side, I have 1 copper, 1 silver, and 1 nitrate ion. Well, on the product side, I have 1 copper, 2 nitrates, and 1 silver ion. So the particles that are not currently in balance, meaning they're not the same value on both sides, are the nitrates. To correct the nitrate imbalance, I would propose to put a 2 in front of the silver nitrate. That does create 2 nitrates, but that also creates 2 silvers. So now we have corrected the nitrate imbalance, but we've created a silver imbalance. So we'll balance the silvers by adding a 2 in front. Now, the other elements have coefficients that we will not be writing. So it is understood that there's a coefficient of 1 in front of the copper and a coefficient of 1 in front of the copper 2 nitrate. But we won't write those values because 1s are understood, though it would be acceptable to write those coefficients on a reagent, but not required. Next, we'll balance the equation in question number 6. This is called a combustion reaction. We know it's combustion because we have a hydrocarbon and oxygen, and it yields carbon dioxide and water. Combustion reactions look similar to single replacement reactions on the reactant side because we have a compound and an element. And they look similar to a double replacement reaction on the product side because we have 2 compounds. But they're neither single nor double replacement, but instead it is just combustion. Hydrocarbon and oxygen yield carbon dioxide and water. Now, to balance this combustion reaction, we are going to again take an initial audit of the atoms present. So we have carbon, hydrogen, and oxygen atoms present on both sides of the equation. Now, on the reactant side, we have 5 carbons, 12 hydrogens, and 2 oxygens initially. Well, on the product side, we have 1 carbon, and then we have 2 oxygens in the carbon dioxide. We have 2 hydrogens, and then we have another oxygen from the water. So this means that currently we have 3 oxygens. Now, when we go to balance chemical equations, in general, you want to leave the hydrogens and the oxygens for last. So we'll initially balance the carbons by placing a 5 in front of the carbon dioxide. Now, when we place that 5 there, we have 5 carbons, and now we have 5 times 2, which is 10 plus 1, or 11 oxygens. Now, the next thing we should balance are the hydrogens. So to balance the hydrogens, what we'll do is we'll place a 6 in front of the water. That will create 12 hydrogens. And now we also have 6 oxygens. So we'll put a 6 here. So 10 plus 6 is now our new total of oxygens, which is 16. So notice that we have balanced carbons and balanced hydrogens, but our oxygens are not in balance. So here we're basically looking for the least common multiple between 2 and 16, which is 16. So in order to change this to 16 oxygens, we'll place an 8 in front because 8 times 2 is 16. And now we are correctly balanced. Again, there is a coefficient of 1 in front of our pentane molecule, but we don't write 1s as coefficients in chemistry typically. Though if you did write a 1, again, it would be acceptable on exam. Question number 7 asks, which equation has a conservation of mass? Now, a conservation of mass basically means we have the same atoms on both sides of the equation, or the equation is balanced. Now, when we look in the first example, we have one sodium on the reactant side and one sodium on the product side. But we have two chlorines on the reactants and only one on the products. So this is not showing a conservation of mass. In the next example, we have one aluminum on each side, but we have two bromines on the reactant side and three on the products. Since they're out of balance, mass is not conserved. In 3, here we have two hydrogens on each side of the equation, but we have one oxygen on the reactant side and two on the product side. Again, matter is not conserved. But in the last example, we have one phosphorus on each side, and here we have 5 chlorines, and on the product side, we have 3 plus 2, or 5 chlorines. So this is showing a conservation of matter. The next question is asking us to find a gram formula mass. A gram formula mass is simply found by adding the masses of all the individual components of a molecule. So here we see that we have carbon, hydrogen, and then we have hydroxide. So here we have 2 total carbons, and then for the hydrogens, we have 4 hydrogens from the H4, and then we have 2 hydroxides. This 2 distributes to both the hydrogen and the oxygen. So then that's 4 plus 2, or 6 hydrogen, and that's 2 oxygen. So now that we know how many atoms we have to look up their masses on the reference table. Now recall that on the reference table, we can round masses to the 10th place. So the mass of carbon rounds to 12.0. The mass of hydrogen rounds to 1.0. And the mass of oxygen, 15.99, will round to 16. Now, once we put this inside of our calculator, we'll get the total mass. So the mass of 24 plus 6 plus 32 should be 62. And our units would be grams per mole. Question 9 is very similar to question number 8, where we're finding a gram formula mass of ammonium chloride. So here we look at the different elements present, represented by 1 capital letter and 0, 1, or 2 lowercase letters. And we have nitrogen, hydrogen, and chlorine. Now we have to account for the number of each atom. So we see that in this formula we have 1 nitrogen, 4 hydrogens, and 1 chlorine. And we'll look on our reference table to find the mass rounded to the 10th place. So nitrogen's mass rounds to 14.0, while hydrogen rounds to 1.0, and chlorine rounds to 35.5. Again, you can see the masses are here in the upper left-hand corner. When we place this in our calculators, we get a gram formula mass of 67.5 grams per mole. Question number 10, we're asked to find the percent composition by mass. Recall that percent composition, this is a calculation, and equations necessary for calculations are found in reference table T of your reference table. So here, reference table T gives us the equation of the mass of part over the mass of whole times 100. In this question, we're looking for the mass of aluminum in aluminum sulfate, and they give us the gram formula mass, Gram formula mass is the total formula mass of aluminum sulfate. So we know that the mass of the whole is 342. And we're looking for the mass of the part. And again, we're looking for aluminum. We know that aluminum has the symbol Al. So we're looking for the mass of all the aluminum in aluminum sulfate. Now, our periodic table tells us that aluminum has a mass of 27. But according to this formula, there are 2 aluminums. So we'll have to take 27 times 2, divide it by 342, and multiply this times 100. Let's put this in our calculator to see what we get. So your calculator should give you a percent of 15.789%, which rounds to 15.8. Now remember that all values will be rounded to the correct number of significant digits on multiple choice. So they may not match 100% with your calculator values. And also remember, always bring your scientific, not graphing calculator to all chemistry classes and tests. The next question has a bit of a reading about a hydrate. A hydrate is a compound that includes water molecules in its crystal structure. During an experiment to determine the percent by mass of water in a hydrated crystal, so this word hydrated means with water, a student found the mass of the hydrated crystal to be 4.10 grams. After heating to constant mass, the mass was 3.70 grams. What is the percent by mass of water in the crystal? For this question, we're going to be using the same equation, percent composition, but we have to kind of figure out what they've given us here. So first they tell us that the hydrated crystal, which is the crystal plus the water, has a mass of 4.10. And then after heating the crystal, what's going to happen is the water will evaporate. So after the water evaporates, we have a mass of 3.70. So that's the mass of just the crystal. Now the question asks us, what is the percent by mass of water? To find the percent by mass of water, we're going to have the mass of part be water, and the mass of whole is going to be the crystal plus the water. So we know our total mass is 4.10. And now we have to find the mass of the water. Notice that we have the mass of the crystal in the water and the mass of the crystal. So to find the mass of the water, we will subtract to get the mass of just the water. When we put this in our calculators, we should find that the mass equals 9.75%, which will round to 9.8.